Section 3.3 Measures of Variation. Now that we understand how to measure the center of data, mean, median, mode, mid-range, we move on to measuring the spread or variability of data. The range is simply the difference between the largest and smallest value. So that's one measure of variation, just from the small to the large. You already know how to compute the mean, so let's get started on example 1. Example 1. Compute the mean and range for each data set below. Complete a dot plot for each data set. Now earlier we learned how to use the stat function to compute the mean, but because this is such a small set, I'm just going to go ahead and type this into my screen. So remember, to find the mean, we sum up all the data values and divide by the number of data values there are. So we have 20 plus 40 plus 50 plus 30 plus 60 plus 70. That's 270, and we have 6 data values. So our mean is 45. And for the range, I just need the lowest the lowest value and the highest value. Well, the highest value looks to be 70, and the lowest is 20, so the range would be 50. In a dot plot, we're just going to put a dot above each value here. So 20, put a dot there, 40, 50, 30, 60, and 70. Okay, let's do that for the next two sets. So for set 2, again, I'll find the mean by adding up all the values. So 47 plus 43 plus 44 plus 46 plus 20 plus 70 gives us 270 again. So we actually got the same mean. And for our range, looks like we have 70 as our high and 20 as our low again, for a range of 50. But let's plot our points. So 47 be about right there, 43, 44. Let's see if we can. So 47, 43, 44, 46, and then 20 and 70. Oh, so that looks a lot different from our previous dot plot. Even though the range is the same, we have a lot of values centered close together, and this is very different from the first one. Okay, let's take a look at the third one. 44 plus 43, finding the mean, plus 40 plus 50. Looks like we're going to get the same mean again, so 45. And the range, let's see, our high value is 50, and our low value is 40, so our range is 10. And if we plot those, so 44, 43, 40, 50, 47, or 46 and 47. Okay, so what do you notice among these three sets? Well, they did all have the same mean, but notice how the mean doesn't tell us enough information. All three of these sets had a mean of 45, but they look completely different. Even the range was the same in the first two sets, but notice that in the first set we're kind of evenly spread out, but in the second set we have a lot of dots concentrated together right around the mean. And then also in the third set, even though it had the same mean as the previous sets, the range was a lot smaller and all of our dots were closer together. So basically, the mean is not enough information about a data set. As you saw, we had 3 different sets all with the same mean, and they look quite different. Even the range is not quite enough. It tells us a little bit more, but we had 2 sets with the same range, and they're very, very different. So we want to explore measures of variation a little bit more. So the range is a relatively easy calculation, but it only uses 2 data values. It can easily be influenced by very large or very small numbers. So if we just change one of those values, it can drastically change our range, which was the difference between set 2 and set 3. Another measure of center is called the standard deviation. Standard deviation measures how far each data value is from the mean and is given by the following formula. The measurement of spread is more reliable because it uses all of the data values rather than just 2. So with the range, we're only using the low and the high, and it doesn't tell us much about the other data values. But with standard deviation, every value is used in the calculation. So our standard deviation, specifically our sample standard deviation formula here, is S equal to the square root of the sum of an x minus x bar squared. So that means you take each value, subtract off the mean, square it, and add those all up, and divide by n minus 1. So we're going to try this in example 2. We'll do it here by hand, and then of course I'll show you how to do it in your calculator. So we're being asked to find the sample standard deviation for each of the data sets in example 1. We'll just do this first one by hand, and then we'll do the other 2 in our calculator. So back here we had 20 through 70 by 10, so that's pretty easy. 20, 30, 40, 50, 60, 70. And the part in our formula that says x minus x bar means take each value, each data value, and subtract off the mean. Well, remember the mean was 45. So we'll say 20 minus 45, and that's going to be negative 25. 30 minus 45 would be negative 15. 40 minus 45 would be negative 5. 50 minus 45 is just 5. 60 minus 45 would be 15. And 70 minus 45 would be 25. Now, what were to happen if we were to add up our values at this point? Noticing that we have a negative 25 and a positive 25, and a negative 15 and a positive 15, and a negative 5 and a positive 5. Well, if I were to add those all up together, I'd get 0, which doesn't tell me anything about spread. And it's because of those positive signs and negative signs, which makes sense, which means some of our data values are higher than the mean, and some of our data values are lower than the mean. So what happens in the sample standard deviation formula is we square each value to get rid of those signs. So negative 25 squared would be 625. Negative 15 squared would be 225, and then negative 5 squared would be 25. So now everything's positive. 5 squared is 25, 15 squared is 225, and 25 squared is 225. Our next step, so we've done this so far, we've taken each data value, subtracted off the mean. Whatever that amount was, we squared it. That's what this represents here, the x minus x bar quantity squared. Now we're ready for this step here. We're going to sum up all of those numbers where we've already taken off the mean and squared. So we have 625 plus 225 plus 25 oops. And we get 1750. Okay, well, let's look back at our formula. There's one more part. We have to divide by n minus 1. So remember, n is the number of data values in the sample. This is going to be 1 less than that. So instead of dividing by 6, we're going to divide by 5, which gives us 350. Okay, so our formula, we did x, we took off subtracted the mean for each value, we squared those, we summed them all up, we divided by n minus 1, and the very last thing we need to do is take the square root. So the sample standard deviation will be the square root of 350. So second square root, which is above your x squared key. And that gives us 18.71, rounded to the second decimal place. Okay, so that's quite a lot of work doing it by hand. So let's go ahead and use our stat function in our calculator to do it for the other few sets. So for set 2, I go into stat, edit, and I'm going to clear this out. I don't need that anymore. And we have 47, 43, 44, 46, 20, and 70. We hit stat, over to calc, one variable statistics, and that was in list 2. Okay, so we already knew the mean was 45 right here, but our standard deviation. Now, I didn't mention this here yet, but remember in section 3.2 we talked about notation between a population and a sample. Populations are going to use Greek letters, samples are going to use regular letters. And notice you have an SX here and a sigma X here, and they're similar to each other, but they're not exactly the same. Because this is a sample, we want to use the S, which is the sample standard deviation. The sigma would be for population standard deviation, so be careful with that. Okay, so for set 2, the standard deviation is equal to 15.87 if we round to the second place after the decimal. And then we need to do the same thing for set 3. So back into stat, edit. Let me use list 3 this time. Let's see, our data values were 44, 43, 40, 50, 47, and 46. And one variable statistics, and this time my information is in list 3. There's that mean of 45 that we knew about. And the sample standard deviation here is going to be 3.46, rounded to the second place after the decimal. Okay, so do you notice anything? Remember set 1, which was the one that was spread out kind of evenly between 20 and 70. And then set 2 also was between 20 and 70, but a lot of the values were concentrated in the middle. What do you notice about those standard deviations? Well, for set 2, it's slightly smaller, indicating that the spread is not as much, the variability is not as much as with that first set, even though the range is the same, because more of the points are concentrated around the mean. That's why our standard deviation is a little bit smaller. Look at set 3. That's where all the data values were concentrated together. Look at how small the standard deviation is. So that lets us know that those points are concentrated and centered closer around the mean compared to set 2 or set 1. So that's the information we get from standard deviation. It helps us in addition to learning about the mean. Okay, so this kind of came up with a calculator, but it's worth mentioning here. So we've been computing the sample standard deviation. If we're presented with data from a population, our standard deviation formula changes slightly, and that's why we have the two different answers in our calculator. So most of it you'll realize is the same. We have the square root, we have the sum, the x minus mu. Remember, mu is the exact same thing as x bar, it's just for population. We're taking those differences and squaring them, and we're dividing by the capital letter N. In the sample standard deviation, it was N minus 1. And that makes a difference, and that's why the values are very close to each other, but why they're also different. So make sure you pay attention to the problem and make the distinction, whether the data is coming from a sample or whether it's coming from a population. Another measure of spread is the variance. The variance is equal to the square of the standard deviation. So it's like we don't do that step where we take the square root. Again, population variance is going to be sigma squared, and sample variance will be S squared. Greek letters for population, regular letters for sample. Because the variance is squared, the units will be different than the units of the original data. So with standard deviation, the units end up staying the same since we square and then undo the square with the square root. So with standard deviation, you're comparing minutes to minutes, or inches to inches, or whatever the measurement happens to be. But with variance, because we don't take that square root, we would be comparing minutes to minutes square, or inches to square inches, and that's kind of hard to compare. So sometimes the units will not be easy to interpret, so for a lot of our calculations, we'll stick with standard deviation as a measure of spread. Okay, using standard deviation. The standard deviation, as you've seen so far, helps us to understand some trends in our data. One basic rule of thumb is that most of our data, about 95%, should fall within 2 standard deviations of the mean. Let's take a look at an example to see what we really mean by that. Example 3. Let's revisit the data about the number of children of U.S. presidents. The mean and standard deviation based on the raw data are 3.55 and 2.91. So this was calculated for you. So the mean, we can consider this a population because there's only so many U.S. presidents and we have information on all of them, so that's a population. So 3.55 for the mean and 2.91 for the standard deviation. So this is the same graph from before, with the frequencies printed above each bar, so it's a little bit different, just the way it's presented. We want to find the number of U.S. presidents that fall within 2 standard deviations of the mean. So what do we mean by that? Well, the mean is 3.55, meaning on average, U.S. presidents have about 3.5 kids. And we know that's just a statistic because you can only have 1, 2, 3, or 4, or so on, number of children, but that's just a numerical average. So that falls somewhere in here. One standard deviation within the mean would be plus 2.91 on one side and minus 2.91 on the other. So let me set that up over here. Let's see what we get. So 3.55 so that takes us to 0.64 and to 6.46. So I'm kind of creating this interval of when I say within 1 standard deviation. So that means I can be 1 standard deviation above the mean or 1 standard deviation below the mean. And that what I'm doing with that is I'm adding the standard deviation onto the mean to be above it, and I'm subtracting the standard deviation from the mean to be below it. So that gives me a margin of from 0.64 to 6.46. But that's 1 standard deviation. We're asked to find the number of presidents, so let me write that down. So 1 standard deviation. We're asked to find the number of presidents that fall within 2 standard deviations. So I'm going to take that 3.55 and subtract off twice the standard deviation, and also we'll take the mean, the 3.55, and add on twice the standard deviation. Now, I realize this is going to be negative, so we'll just call this 0, because our data doesn't make sense on a negative scale for this particular scenario. But here, 3.55 plus 2 times 2.91 gives us 9.37. So this is 2 standard deviations of the mean. Well, let's see if it holds true about 95% of our data being within 2 standard deviations of the mean. So I'm going to add up all the frequencies that fall in this interval. So I can add up the 8, the 16, the 10, and the 6. A little bit of a discrepancy of whether we should include the 1 or not. That's between 8 and 9. Let's leave it out and just see what we get. So we get 8 plus 16 plus 10. I don't think I'll add it in, because if I'm greater than 8 but not quite 10, that means 9. And being that these are children's integers, so we'll add that one on. So 8 plus 16 plus 10 plus 6 plus 1 equals 41. But there are 43 presidents. And that represents 95% of our data. So it's not a hard and fast rule, but it's kind of like we mentioned before, it's a rule of thumb. This is what generally happens with most data sets. So when you're talking about within one standard deviation or 2 standard deviations, you add the standard deviation to the mean and you subtract it off to get that interval of where you want your data value to fall. Okay, some other rules about how our data falls. And helping us with interpreting standard deviation is the empirical rule. The empirical rule states that for data sets that are approximately bell-shaped, the following are true. So bell-shaped is usually going to be that symmetric data where it's steep. Most of our frequencies are concentrated in the middle, and it kind of tapers off into the tails. So the empirical rule states that 68% of all data values fall within 1 standard deviation of the mean. About 95% of all data values fall within 2 standard deviations of the mean. We just saw that. And about 99.7% of all data values fall within 3 standard deviations of the mean. Let's take a look at number 4 and see how that goes. Again, we're going to take a look at data from a previous problem. Let's re-examine the data about the number of pups that female great white sharks have in a lifetime. The mean and standard deviation for this data are 7.13 and 1.89. So not that it is a distinction to what we're going to do with standard deviation. Let's just think about whether this is a population or a sample. We're probably never going to reach all the sharks in the entire world. So this is definitely a sample. So for my notation, I'm going to use X bar since this is a sample and these are my statistics. So X bar is 7.13 and the standard deviation denoted by S is 1.89. So they gave us that information. So first we're going to find the number of pups within 1 standard deviation of the mean. So to find that interval, I'm going to take the mean and subtract off the standard deviation, and I'm going to take the mean and add on the standard deviation. So that's from 5.24 up to 9.02. So that means I'm going to take this one and this one and this one and this one, that 4. Let's see what percentage of data it actually represents. So this is the interval. I just want to check to see if it fits with the empirical rule. So for my frequencies, I'm adding up 11 plus 17 plus 17 plus 11. And that's 56. And we looked at 80 sharks, I believe. That's 80. So let's see what proportion or percentage of our data that represents. So 56 divided by 80 is 70%. And what did our empirical rule say? 68%. So about right. Remember, it's kind of approximate, but that kind of works. Let's see what happens with 2 standard deviations within the mean. So I'll take the mean and subtract off twice the standard deviation. And I'll also take the mean and add on twice the standard deviation. So that's 3.35 and 10.91. So this time 3.35. So we'll take these, this, and this, and we'll also take this one, and oh, I'm running out of room here, but if you were to add those up, you see I think it comes to about 90%, which is sort of close to that 95, if not quite. Let's go ahead and find what the interval would be for 3 standard deviations within the mean. So we'll take the 7.13, subtract off 3 times the standard deviation, and we'll take the 7.13, the mean, and add on 3 times the standard deviation. We get 1.46 and 12.8. If you look at your graph, by the time we go that wide, we pretty much have the majority of our data. So the empirical rule, about 68% within 1 standard deviation, about 95% within 2 standard deviations, and almost all of our data, 99.7%, within 3 standard deviations of the mean. Now the empirical rule gives us those specific percentages for data that falls within 1, 2, or 3 standard deviations of the mean, but the data has to be bell-shaped. What if we're interested in only 1.5 standard deviations from the mean, or 2.75 standard deviations from the mean for any data set? For this purpose, we use Chp3Sec3STAT's theorem. It is only an approximation. It's not as accurate as the empirical rule, so the limits are a bit lower. Here's Chp3Sec3STAT's theorem. It says the proportion of values from a data set that fall within k standard deviations of the mean will be at least 1 minus 1 over k squared, where k is a number greater than 1, but not necessarily an integer. So just like before, we were stating so much data fell within 1 standard deviation of the mean, and so on and so forth. This is it's kind of saying the same thing, but it's a little looser. The limits aren't as strict, but it's allowing for that, and that this can be used with any data set, whether it's bell-shaped, whether it's skewed to the left or skewed to the right. So that's why the limits are lower. Let's take a look here. If we are interested in the proportion of data values that will fall within 1.5 standard deviations of the mean for any data set, we let k equal 1.5 and simplify the expression. So knowing that I want to be 1.5 standard deviations away from the mean, when I plug this into this expression here, it'll tell me the lowest proportion of data values that will fall within that range. So I take 1 minus 1 over 1.5 squared, and I'll throw that in my calculator. And I get 0.556, which I prefer a decimal for a number like that. So if you hit math and the first entry arrow fraction, that'll turn that into a fraction for us. So that's 5/9. But you can if you prefer, you can write the decimal. They're equivalent. That's fine. Okay, so what Chebyshev's theorem is saying is at least 56% of our data is within 1.5 standard deviations of the mean. Now, it's very possible that there's significantly more, but this is at least the bare minimum. That's what this is saying. At least 56% of our data is contained within 1.5 standard deviations, no matter the data set. So that's what we get from there. So let's put that here. So at least 56% of the data values lie within 1.5 standard deviations of the mean. Okay. What if k were equal to 3, meaning 3 standard deviations within the mean? Well, remember with the empirical rule, we got 99.7, almost all of our data. Let's see what happens here with Chebyshev's theorem. So I'm going to take my little formula, my expression rather, 1 minus 1 over k squared, and I'm going to put in 3 for k. So that's 1 minus 1/9, or 8/9, which is 0.89. So this means at least 89% of our data is within three standard deviations of the mean, and that's for any data set. But we already noticed that for bell-shaped data, it's going to be much higher. It's going to be 99.7. Okay, one other example related to Chebyshev's theorem is example 5 here. The mean price of houses in a certain neighborhood is $150,000, and the standard deviation is $10,000. Using Chebyshev's, missing a Y there, Chebyshev's theorem, find the price range for which at least 89% of the houses will sell. Okay, so we have a little bit of work to do here. Actually, we kind of have done it already. We know that 89% corresponds with 3 standard deviations. Remember, it doesn't matter what our data looks like. Chebyshev is making this this assumption for any data set. So what I want to do is find the prices within 3 standard deviations of the mean, since I know that 89% corresponds with k equal to 3. So just like we did before, I'm going to take the mean, that 150,000, and I'm going to subtract off 3 times the standard deviation. And I'll also take the mean and add on 3 times the standard deviation. So 120,000 and 180,000. So what we're saying in here is at least 89% of houses will sell between 120,000 and 180,000. Okay. If for some reason, if we had a different percentage here and we didn't automatically know, let me just mention this in case it comes up in a homework problem. If we didn't know what K was automatically, we could back solve to find that. So let's say I didn't know at all. I hadn't done the previous work. I would set up 1 minus 1 over K squared, set that equal to 0.89, and then solve for K. So if I were to subtract 1 from both sides, I'd have 1 over K squared equals negative 0.11, and then take the reciprocal of both sides, and this is where I'd want to carry as many decimal places as possible in my calculator, and then take the square root and there we get something pretty close to the 3 that we knew was coming anyway. So if it's not something really obvious like that 89%, you can look at I mentioned before, standard deviation depends on the units of the original data. And for this reason, it makes it hard to compare standard deviations from different samples or populations. So if one sample is measured in inches, but another sample is measured in feet, or not necessarily both linear measurements, but maybe one is inches and maybe something else is cups, and we're interested in how they vary, we can't compare that. That's not comparing apples to apples. What the coefficient of variation does is it makes the standard deviation a percentage of the mean, and then we don't have to worry about units anymore. So we're able to compare two samples even if they're very, very different. So the coefficient of variance is defined as whether it's a population or a sample, the standard deviation divided by the mean times 100. Standard deviation of a population over the mean mu times 100. So we're going to calculate the coefficient of variation for each set here. And you'll notice already that they're very different. Set A is in dollars and set B is just regular numbers. Maybe that could be test scores or weights of junior high kids or anything like that. We don't know where it comes from, but they're obviously not in the same units, and the coefficient of variation is going to allow us to compare standard deviations. So I'm going to go ahead and put this in my calculator like before using my stat edit feature because it'll give me the mean and standard deviation right away. And remember, you can go up and clear if you highlight the list name and come back down. So we have 1.23, 1.55. Okay, so there's my first list entered in. I'm just going to do these at the same time. And 119, 145. Okay, so I have both of my data sets listed. So list 1 is my dollar amount, and list 2 is set B, which we don't know where it comes from, but just the regular numbers. So again, I'm going to do stat, and it would be tempting to do two variable statistics, and you could, but that's really for comparing two data sets that have something in common, and these are actually very distinct and different. So I'm just going to run one variable statistics on each set independently. So first, for that first set, I have for set A, the mean is 1.865, and and we're going to assume this is a sample. The sample standard deviation is 0.555. And I'm going to try to carry as many decimal places of that as I can. And then for set B, so stat, one variable statistics on list 2, X bar is 112.21, some extra decimal places, and the sample standard deviation is 12.84. Okay, so let's get the coefficient of variation here. So the coefficient of variation for set A is the standard deviation divided by the mean. And that gives me times 100. So that's 29.78. And the coefficient of variation for B would be standard deviation over the mean. Times 100. Okay, so now these are percentages, and we can say for set A, 29% of the variability here, or the explanation of the variability, we can say the variability is 29.78% of the mean, whereas on set B, it's 11.46. So even though these were drastically different data sets, one was in dollars, one was just regular numbers, we can look at these and say, well, set B, whatever that data comes from, has a smaller measure of spread than set A. And it's because we got down in percentages rather than the units of each individual set that we were able to do that.